there's an A, you don't know anything about that A, because on the use side, the user can pick an arbitrary Haskell type for that A, as we just saw. So that means you can't do anything about it, with it. So in particular, you can't pattern match on it because you don't know the constructors, and you don't have any functions that operate in it. So the only thing you can possibly do is pass it on to somewhere else. And this last point here, if a function result has polymorphic type, then except for undefined error, you can only try to build one from the function arguments. So we already talked about that. There is no, except for undefined, there is nothing of type A, just A, because the A must come from somewhere and you don't know anything about A, so there's no way to produce an A if you have no other information. Okay. And this is now, I mean, I already briefly talked about that, but now we can go about it in more detail. So how many functions do you think have this type? I mean, we can just start implementing some. Let's say foo1. What was it? Int. Okay. So can somebody give me a possible, this is annoying. Just 1 second, please. Okay. Right. So I mean, fine. We all saw it. So this would be a possible way, but can somebody give me some other possible implementation? How, given two ints, x and y, I can produce two ints? Yeah? Yeah? I could do this. Anything else? Any other suggestions? I'm sorry? Yeah? Okay, maybe one more. One more, maybe. I mean, I can also do something. I mean, I can do x plus y plus 42 and y minus 2 times x, or whatever. Right? So the point is there are infinitely many, or almost infinitely many, possible functions with the signature. Right? I mean, instead of doing +1, I could also do plus 519, and I don't have to use the same. I could do +3 and -4, or, I mean, there are lots and lots and lots of possibilities. So just knowing that a function, I mean, if somebody gives you, says I have a cool function foo and it has this signature, but I'm not telling you how it's implemented, then you don't have much information. I mean, except for, I mean, you don't have no clue. It could be any of these implementations. Okay. But now let's look at this signature. Can somebody give me a possible implementation for this? So I have two A's, x and y, and I must produce two A's somehow. So what can I do? Yep, you could swap. Anything else I could do? Yes? Anything else? So I mean, I have a, I mean, what do I need? I need two A's. What do I have? I have two A's, X and Y. So so what else can I do? I mean, there's not much I can do, but there are at least two more things I could do. I mean, how many A's do I have at my disposal? Two. And I need two. So for each of the two I need, I have two options. So there should be four. Right. So I have XX. Sorry. And I claim that this is all you can possibly do, except if you throw an error. I mean, use error undefined. That's, I mean, maybe I should, this is now didactically very bad, because now it looks as if there are just as many. So let's add one more here. I mean, I can also here, for example, completely ignore the X and Y. I just want to demonstrate, so here it really goes on and on. But I claim that this here is I claim that this is a complete list. And there's nothing more you can do. Because what do you have to do? I mean, you have to come up with two A's for the result. You don't know anything about A. You don't know it's in, so you don't have constants. You can't write 7 or something. You don't know whether you can add X and Y or subtract them or show them or anything. You have no information about X and Y except that they are of the same type A. But you don't know anything about A. So the only possible way to produce an A is use one of the two. I mean, you have the X and the Y, and that's all you can do. So you need two A's. So I mean, for both that you need, you have these two options. You can pick X or you can pick Y, but you can't do anything else. So those four possible implementations of bar are the only four ones with this signature that you can write in Haskell, except if you use undefined something. Okay? So this comes back to why, to the question also in the chat, why it might be good to use a more general type signature, because it makes it easier to implement it, because you have fewer options, so you have also fewer opportunities for mistakes. And the compiler can help you better. So in general, it makes sense to write as general a signature as possible. And I mean, the extreme example is function, but I already did that on Monday. If you have this, then there's only one implementation. You need to produce a B and an A. You have a B and an A and a B, and you don't know anything about A or B. So the only B you can possibly produce as a result is Y, and the only A is X, and there's nothing else you can do. So in this case, there is only one possible implementation with this signature. So the more general, and note that this here is a specialization of this one, and this is a specialization of that one. So in general, the more general the signature, the fewer possible implementations you have. And in extreme cases, I mean, it's not always the case that there's only one, of course, but I mean, sometimes we want integers or whatever. But in general, the more general the signature, the fewer possible implementations. And that's easier. It makes it easier. I mean, because if you have an int, there are all sorts of stuff you could do with it. You can square it, you can double it, you can subtract 1. But if you have just an opaque type that you don't know anything about, then there's nothing you can do except like take it as it is and put it somewhere.
Is that the reason the compiler forgets the runtime doesn't know what any type?
I think the reason is that it's not needed at runtime because the compiler makes sure that it all fits together. So at runtime you don't need it. You know that everything is type safe, so you know you won't apply a function to something that it can't handle. Okay, other questions at this point? So most general type, and in general it's better to use it because it makes your life easier as an implementer.
The types are help for the programmer. Once the coder did his thing, you can, the compiler checks that everything is right, and there's no need to like increase the runtime just to have those. So the compiler removes everything.
Mm-hmm. Right. Okay. That's that example. So, as we saw, in general, parametric polymorphism severely restricts how functions can be implemented. So we saw in this example, the more general I got, I mean, the more parametric, the more polymorphic I became, the more restricted I was in my possible implementations. So it's good if something you do can be generalized if you actually do that, because that prevents you from making errors. Because you are not tempted to use like special features of int, for example. Yes?
So Haskell doesn't have a global type, like in OP there is the object.
No, it doesn't.
So in this case, being more generic restricts it than
Yes.
in OP where you're able to do more things to more generic.
Right. But even in OOP, I mean, if you just get an object, you can do fewer things with it than with some cool class.
If you specify an object, you are more restricted. So this time is the other way around. Like
Yes, okay.
Yeah.
I mean, this would correspond to if you in C# only get an object as an argument, there's very few things you can do with it. I mean, there are some things you can do with every object, like show it or so. Yes, exactly. But fewer things. So I mean, similar in OP, just the other way around, I suppose. If you have something of type whatever class, I don't know, integer in C#, then you can do numeric stuff. If it's only object, you have fewer options what you can do with it. And here it's similar in this sense. Yes, and there's no type in Haskell where everything belongs to like object, and there's no hierarchy. I mean, they are all like disjoint. In Haskell, everything has one type. There's no subtyping. So it's not like in object-oriented programming where something can belong to a class but also to a superclass. Everything has one type. I mean, one most general type. And also, if you see something, I mean, if you have a library you see on Hackage that something has a polymorphic type, then you know that the implementation, even if you don't look into implementation, you know the implementation can't do anything with an argument of this type except pass it on, because it doesn't know anything about this. And sometimes it's even possible by just looking at the signature to infer certain properties of the function it will have. And that's sometimes called parametricity. So in principle, one example we saw in this bus thing, I mean, there you can't only infer certain features, you exactly know what it does just from the signature. But there are less extreme examples. For example, we saw the map for lists. So given a function from A to B, maps a list of A's to a list of B's. So the signature alone doesn't completely specify the implementation. There are things you know about it. For example, I mean, it produces a list of B's, but how must it get those B's? And the only thing it can do, I mean, what does it get? I mean, if you have to implement that, all you get is a function from A to B and a bunch of A's. So the only way for you to produce a B is to take some of the A's you got and apply the function to it. So, I mean, even though you don't know exactly how this is implemented, you do know that you get a list of B's where each B is the given function applied to an element that was in the list before, because there is no other way to get a B. So you do know must produce a list where all elements are obtained by applying the given function to elements of the original list. But of course, you don't know, for example, how that the result list will be as long as the original one. I mean, you could, for example, just always return the empty list, or you could like repeat every element twice or whatever, or only consider the first 5 A's or something. So I mean, this you can't see from the signature, but you can see amazingly much from the signature alone. Right, and this is now a bit weird example, but maybe not bad. So let's try this. So let's say we want to write a parser for stuff, and so it gets a string, and you think you want to like be able to parse arbitrary things. What was the example? False and 0. And this gives an error. And it's always with polymorphic types, always the caller can decide for which to, how to instantiate the type variable. So if I'm using this parse function, I can pick A, what I want. So, and so for example, I could say I want A is double or whatever. And then the implementer of the parse function would need a way to no matter what type I pick, to produce a value of that type. And that's just not possible, as we have discussed before. So the only way to implement something with this signature would be undefined or error. So this just doesn't work. So this is the wrong way to do this idea that you want to be able to parse like things of different types. So this can't work, but there are ways to do something like what maybe you would have wanted to achieve with something like that. So one option is we talked about some important types in Haskell yesterday, and let me just do this here, show you. There is another important type that we haven't seen yet. That's called either. So data either, 2 type parameters, A and B. And the idea, as the name said, and it has 2 constructors, either left A or right B. So an either A, B can either be an A or an B. So if you have an A, you can use the left constructor to get an either. If you have a B, you can use the right constructor. So if you want a type that can be this or that, then you can use either. So we can, I don't know. So for example, either string bool or whatever, then you left Haskell. And right true, for example, would both be of type either string bool. So you could, for example, fix this example here by saying either bool int, and then if you see the false, you return a left false, and if you see a 0, you return a right 0. I mean, that's still bad because if you see something else, it will crash, but at least now it compiles. So now we can, for example, try it with false, and we get left false, and we can try it with 0, and we get right 0. But if we try it with true, then it crashes because the pattern match doesn't succeed. So it gets a string, it tries false, that doesn't fit, tries the next equation, 0 also doesn't fit, and then there are no more equations, and then it crashes. Right, but that would be one way. And another way, I'm not sure I have to do this now by hand. So you can also define your own type. So you could say, for example, define a value data type that can either has a value constructor bool and vint of int. And of course, you could add more types. So this is like, either is generic, works for each 2 types, but sometimes it makes sense to basically use a type that behaves like either, but has more specific names to make it clearer for the user what the intention of this type is. But same idea. And a lot of libraries on Haskell use something like that for their parsers. So for example, there's a very popular library that we'll probably also use later in the course, I'm not sure, called ASON, and that's for JSON parsing in Haskell. And then you can parse strings into JSON values, and basically what you get after parsing is something like this. So there's a Haskell type with several constructors for all the possible JSON values, like int and bool and objects and so on, and lists or arrays. So that's a common technique if you basically have like a polymorphic, polymorphic is the wrong word, but something like a polymorphic result type. You define a type that contains all possible cases. Okay, are there any questions at this point? Because then we would go to overloading type classes next. Okay. So there are like two versions of polymorphism in Haskell. So until now we talked about parametric polymorphism. So you have one implementation, like our first function. So it's the same code, like one implementation that works for many, many different instantiations of the type parameters. And then there is so-called overloading or ad hoc polymorphism that allows you to use the same function name in different contexts with different implementations. So that's more like, it's very similar to interfaces in object-oriented languages. So where you have an interface and so that defines functions with certain names, and then for different classes you can give different implementations. So that should be more familiar to most of you, probably the second. And what are interfaces in other languages or traits in Scala, for example. In Haskell it's called a type class. So it's a class, but it's like, it's not an object-oriented class, so don't get confused. It's more, if anything, it's more like an interface. So an example is the IOG class. And maybe I should just, I don't know, this is annoying with the error, but I can make the error go away by saying the error was annoying me, so now if we do pass through, it still crashes, but now we get an error message, at least a custom error message, can't pass through. And so I just added this catch-all case, which uses the error function we talked about. And here I'm demonstrating the dollar, because otherwise I would need parentheses around my string here, right? And we saw the ++ yesterday for concatenation. Right, now I wanted the IOG class. Let's just hide IOG from the prelude. So let's say, this is built in the prelude, but we could define a type class in Haskell, IOG-A. The syntax is like so. So we say class name, again capital letters like for types or for constructors. And then it can have, in standard Haskell, one type parameter. So this is now a class A, a type A can be an instance of class IOG. And now I can define what it means to be an instance of this. And in this case, it has two. So I can give signatures that somehow involve A. So I can say, given two A's, I want a function from A to bool. And I want another function, equal and not equal to bool. So this would be a definition of a type class in Haskell. So this, that's, as I said, you can think of it as an interface in object-oriented programming. And now we can make types instances of type classes. And let's say we want to make Booleans instance of type class, of that type class. So then the syntax would be instance eq bool where right. And now I must, for the special case that A is bool, implement those two things. So I must implement a function of type bool to bool to bool and another function of type bool to bool to bool, where A is now bool. So how would I implement this for bool? I mean, that's like a repetition of yesterday. We saw how to implement stuff for bool. And there are only two cases, true and false. So I can, for example, say true equals true is true. False equals false is true. And anything else doesn't equal each other. And for the non-equal, I can just say x not equal y is not x equals y. Why is this now? Okay. That's interesting. Okay. Right, so this would be a possible implementation of this. So now I have made type bool an instance of class eq. Another thing we can do is we can show you, I can, for example, now provide an instance for lists. So I can say instance, so I want to say if I can compare A's for equality, I can also compare lists of A's for equality. So the syntax for that is as follows. So this says, I claim that if I have a type A, that's an instance of the eq class, then list of A's is also an instance of the eq class. So that means now in the definition of the two operators, I can use the fact that A is of type eq. So how would we compare two lists? Well, the empty list equals the empty list. And if we have two lists that are not empty, then what can I do? I mean, they are equal if the heads are equal and the tails are equal. So, and in order to decide whether the heads are equal, let me just write it first. So this ampersand, I think we haven't seen, but that's logical AND. So we talked a bit about logical OR as an example, so this is logical AND. So how do I compare, decide whether two lists are equal? They are equal if and only if, I mean, two non-empty lists, if the heads are equal, so x equals y, and if the tails, recursively the tails are equal. And for this first part here, x equals y, I mean, the x and y are of type A, so I need to know that I can compare A's with each other. Therefore, I need this condition here. And now, what's the remaining case? The only case I haven't done is the empty list to a non-empty list. Yeah, I could say, I mean, I could again say in all other, sorry, there are two more cases. So I can just say in all other cases they are not equal. And what's this now? Right. So this is now the equals. And now I must say when two lists are not equal, but I can make my life easy again. Not. Right. So of course, both those instances, I mean, I did that now for demonstration, but this is of course already predefined in the Haskell prelude, so you don't have to do that by hand. So Haskell already knows that Booleans are an instance of equal, and it knows that lists are an instance of equal provided the elements are an instance of equal. So then one thing we see is that in both these examples we have, I mean, the not equal case was always like the same boilerplate. So what we can do is we can provide so-called default implementations. So we can say x not equals y is not x equals y.
No, that's useless.
That's useless?
Yeah.
Okay. Right. And I can even do the opposite and say x equals y is not x not equals y. So this is so-called, so in the class definition I can provide so-called default definitions, and they will be used if I don't explicitly use that. So because I now have a default definition for the not equals case, I can remove this here. Sorry, and this. I removed too much. What now?
It's indented.
Oh, it's indented. So yeah, indentation is crucial in Haskell. So now the error was that I had one additional space there, and that gave me a parse error. So things that are like logically on the same level must also have the same indentation. I think I could indent everything by 2, but then I must be consistent. So, and because I started doing my top level definitions without any indentation, I must continue like that. Same is here in these equations. I can't just put or I can? No, I can't. So I can't just, I mean, things that belong together, like on the same level, they must be indented in the same way. Right. And of course, so there are these default implementations. So in this case, because if I have defined equality, I can always define inequality by just negating equality. I don't have to implement both. Now, of course, I also have a default implementation for, I mean, I have one for both. So the compiler wouldn't complain if I removed everything. So if I, let me just comment that out for a second. Sorry. Go away. Right. Let me reload. So I reload it now, and I don't even get a warning. So the compiler is perfectly happy, even though this is now, I mean, I haven't defined anything. So the compiler is happy because I have a default implementation for equal and one for non-equal. So it's happy, but obviously this can't work because now I haven't told it anything about how to compare Booleans. And if we now try it, true equals false, then it just hangs. Because if you, and I have to control C to get out, because now it just loops. I mean, it tries to evaluate this, uses the default implementation, tries to evaluate this, uses the default implementation, so it forever is round in circles. And so that's a bit bad. I mean, not a nice situation. But there is something, a pragma in Haskell to make this better. That's the so-called minimal pragma. So I can say, I hope that's how it works. It's how it works, but I don't get, hang on, sorry. I use that so seldom, I never know how that actually is done. Just, Sorry, that's of course
Yeah.
is a bad example because I need something, some class. Let's say eq. Oh yeah, I forgot the hash. Right, I forgot the hash. So these pragmas always have curly brackets, minus, and then a hash, like so. Otherwise, it's just a normal block comment. So in order to use this compiler pragma, I need this. And now if I reload, I hopefully do get a warning. Yes. So this minimal pragma tells the compiler, it says, I mean, what we saw in this example is in order to have a proper instantiation of class eq, you don't need to necessarily implement both equality and inequality, but one of them. Because the default implementations refer each other, so if you implement none of them, then it loops forever. So you need either, I mean, at least eq or, I mean, equality or inequality. And that's exactly what this pragma says. So it tells the compiler minimal complete definition is equal or non-equal. And once I added that pragma, now when I reload, I still don't get an error, but at least I now get a compiler warning. No explicit implementation for either equals or non-equals. So this is better, and this is also how it's done in the prelude. And you can have more complicated. You can also separate things with comma. So you have the vertical bar and comma. So it can. I mean, it's not always just one. It can be. You either need to implement method 1 and 2 and 3, or method 5 and 7, or something, or method 9. Right, so that's that. Let's just check the slides. Forgot anything? So I showed you the bool example. I showed you the list example. Explained this. Right, so I mean, so the class type can be an instance of a given class or not. So you get like a subset of all types, of those types that are actually an instance. And that we already saw that, I mean, if we now ask for the type of, okay, sorry, first I should fix this here and remove this again so that we do have our implementation. So now the warning is gone and now the equality should work again. Right, and if we ask for the type of this equals, then we see what we have already seen yesterday and day before yesterday. So now the type of this function is from A to bool, but in addition it has this so-called class constraint with the double error. So this now says equals is a function from A to bool, provided type A is an instance of the eq class. And we saw examples of that yesterday, plenty, I think. I mean, for example, lm. Oh yeah, this is now because I hid this. So normally it wouldn't look so complicated. So this is now the official eq in the prelude. So it would say for a container type T and type A that implements equality, if you have an A and a container of A's, then it tells you whether the given A is in the given container. Okay. And that we already saw that not only the class methods themselves, but also, I mean, I just showed you lm, for example, and the lookup yesterday. So functions can have these constraints. Here's another example. I'm not sure whether I have to implement this, but maybe we can implement it and then also see that the compiler automatically infers this. So all equal. So the idea is we have two lists, one list, and we want to see whether all the elements of the list are equal to each other. So I can just implement that. So for the empty list, yes, because there are no elements, so it's trivially true. If it's just a singleton list with one element, it's also trivially true. And if it has at least two elements, Well, then I must check that x equals y and that recursively all equal in the list y ds. Why is that now? Okay. And now we see the compiler automatically infers this type signature. So it sees that, okay, I don't need the x here. So it also automatically deduces that I need equality in elements for this implementation. So we see that the Haskell type inference algorithm that always derives the most general type, it also understands type classes. So it also works with type classes and infers the necessary constraints. So by just writing the code without writing the signature, it gives me the correct signature. I need equality on A's and then a list of A's, and I can decide whether all elements are equal. So we can try it out if we want. All equal. What do we? I mean, for example, you can take a string x, 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 x. Oh yeah, sorry. This is now the, unfortunately, not the built-in equal. So I must do something for which I know it, and that's unfortunately only Boolean. So let's say true, true, true. It's true, but if one of the true is a different one, then it's false. Okay, almost time for a break, I think. We'll just check. So this we have already done. Okay. Okay. So let's look at this example. Maybe I should write it. No, I shouldn't, then probably it will be given away. What?
Yeah, you will give it away.
It would give it away. So let's just look at the slide. We have a function that takes, has two type parameters, a and b, and takes two pairs of an a and a b and produces a string. And the implementation is as follows. If x1 equals x2 and y1 equals y2, then show x1, and otherwise the string different. So can you say what constraints I need for this? So what, I mean, if I now type that into my editor and the compiler would automatically suggest the type signature, so what constraints would it pick there? What constraints do I need for this implementation? Any suggestions? Yes? I'm sorry?
EQ.
Yeah, for which type? Elements of which type am I comparing for equality? No. I'm using equality comparison here and here. So what's the type of x1? x1 comes from here. So I'm using equality here and here. So I apply it to x1. x1 comes from here, it's pattern matched here, and this is from here, so it's an A. So x1 has type A, so I need equality on A. Here, I need it for y1 and y2. They come from here and here, so they are of type B. So I also need equality on type B. And finally, anything else?
Sure.
Exactly. I show x1, and x1 is of type A, so A must also be an instance of show. So the solution is this. So we need equality on A, equality on B, and show on A for this to work. And the compiler will automatically infer that. Okay? Question?
But you said that the polymorphic type signature can tell you what property, the function. So when you add a class, does that mean you're adding extra properties on the original properties that are in the function's signature?
Yes, so by adding constraints, you basically have more, suddenly you know more about the type. I mean, earlier we said, for example, if you can't write, I mean, for example, if we want to implement a function, I hope I understand you correctly, but I think I do. So let's say we want to write a function from A to string. Just like this, with this signature. Then, because I don't know anything about A, there is no way I can somehow use the A to produce a string. So all I can do is completely ignore the A and say something like, whatever, Kenya. So I mean, I know from the signature like this that the A it will be a constant function. It can't possibly make use of the given A because I don't know anything about that. So that I don't know how to use the A to make a string. If, however, I have this show A constraint, then suddenly I have more options because now I can use whatever is in the show class. So now I could, for example, whatever, I mean something stupid. Kenya says hi to, something like this. So now suddenly, so now I have more tools at my disposal. So if we compared what we said earlier, so adding class constraints somehow makes it less general and makes the implementation more difficult in the sense that you now have more possibilities. Any other questions?
So plus is like a collection of properties.
Yeah, I think they are called methods.
Yeah, but you can think of them as behaviors that you are allowing, that you're giving the type. So you type like as every time you create a new type, it has like no default behavior. So by implementing all these instances, you are giving all the behaviors of each instance.
Mm-hmm. Right, and it can be one or more. I mean, we saw an example now with 2, equality and inequality. It can be arbitrarily many.
Yeah.
It can even be 0, I think, with some extension, but at least 1, I mean 1 to many. And they can have like arbitrary signatures. I think they should mention the A somewhere, but it can be anywhere. Or left-hand side, right-hand side. So we will see examples, more examples. So this is just this equal and this default stuff and the minimal. So I showed you all of that. I didn't show you the plus I. I mean, earlier, of course, but not for this special case. So let's just do colon I on our eq. So if you ask for information on a type class, then you will basically see the definition. So class eq A, so this is just what I wrote, and you also will see the minimal, and you also will see the known instances that are in scope at the moment. So it also shows you that booleans are an instance, and if an A is an instance, then lists of A's are also an instance. So that's often quite useful. I mean, often you use some third-party library and that you're not intimately familiar with, and there are some weird constraints that you don't know, and sometimes it's useful with colon I to see whether some types you are interested in are an instance or how you can. So this colon I is really useful.
What's the same?
I'm sorry? I think we talked about this unsafe perform IO earlier, and that you can basically cheat with the type system. And there's an extension called safe Haskell that disallows such features. And this means that this class is in the subset of safe things. So nothing fishy can go on. So I'm not using unsafe perform IO. So if somewhere I would use that, then that would go away. Okay, other questions? Okay, this I'm not sure. So I mean, classes and types are 2 different things. So you can't write something like this. I mean, you can't use them in signatures. I mean, eq is not a type, so it doesn't make sense to write a signature that says eq or eq A or something. I mean, they have this. I mean, constraints and types are 2 different kinds. 2 of a kind. And so we saw the syntax. So if you have a constraint, then it goes on the far left with a double arrow. If it's only one like this, and if it's more than one, you must put them in parentheses. Right. And maybe we're now going on for a bit more than an hour. We should have a short break, 10 minutes. Okay. classes that are defined in the prelude. So some of those we have already seen. So eq we just took as an example. So comparing for equality or inequality. And so in Haskell, equality is structural equality. So if we saw with, if the constructors basically match. And there's nothing like we alluded to that earlier, that in objects, for example, you can compare objects for equality, so like pointer equality, there's no such thing in Haskell. And most data types that we talked about already do support equality. So if we I showed you this :I, so now it's a bit annoying because let me just remove this hiding here, and then I comment my definition of eq so that I don't get a clash. Oh, and I think I must also comment out the instances. Okay, now it should work. So now we are using the built-in, the prelude eq again. And if I ask for for info on that, we saw before that it gives us instances, and we see here in the case of eq, there's a long list of things it knows that are equal. So this, for example, is the one we did by hand as an example, and somewhere here is the other example we did, bool, but we see also for like ints and characters and doubles and floats and all sorts of types, it's already predefined, and also for tuples and pairs. So here, for example, if we know that A is an instance of eq and B is an instance of eq, then also pairs of A's and B's are an instance of eq. And the same for like tuples with more, higher arity. Or maybe, okay. So that's eq. But prominently or importantly, function types don't support equality. So you can't compare two functions for equality. Because that would be like infeasible to compute. Maybe you could say two functions should be equal if for the same input they give you the same output. But of course that's impossible to check. To write a program that checks that, at least for functions with infinite domains, codomains. Okay, then we have OR. I think we also already saw that. Just a second. Right. So there's something new here that we haven't seen before. So this says for so class ort requires in particular that it must be eq. So this says we define a class ort A, and a condition to be an instance of ort A is you must first be an instance of eq A. So each type that has ort also has eq. And then there's a bunch of methods here. So the unsurprising ones can less than or equal, greater than or equal. Then max and min. Max we saw in an example yesterday. And then there is this compare. And here on the slide you see the definition of ordering. So ordering is a type with three constructors, so it has three without arguments, so it has three values, LT, EQ, and GT, so standing of course for less than, equal, and greater than. So for example, we can try it out, compare, for example, for characters, A and B, I get less than. If I have D and B, I have greater than. And if I have D and D, I have eq. And if we ask for information on ort, we will also see lots of instances. And here, minimal complete definition is you can either implement compare or less than or equal. So if you want to write your own instance for class ort, you don't have to implement all of these, it's enough to do compare or less than or equal. So there will be default implementations for all the others then. And again, we see there's a bunch of predefined things. So for example, I mean, we have something for characters somewhere here, and we will have something for lists. That's hard to find, of course. We missed it. Here, right, the very first one. So now we know that because characters are odd, and if the element type is odd, also lists are odd. That means, for example, in particular, that strings are odd. And that is lexicographic. I mean, the way it's implemented for lists is lexicographic comparison. So I have, if I have compare whatever, so, but if it's so it's, I mean, like it would be in a phone book, or, I mean, the usual way to sort strings. And other lists. I mean, it doesn't have to be character. I can also compare whatever. For example, this. So it's lexicographic ordering. And I think for tuples, it's also lexicographic. So first, the first element in a pair is compared, and if they are equal, then you look at the second one.
We have a foundational question, I think.
Yes?
Someone asked, can you use functions instead of classes? So I'm guessing they are asking if you can just define the functions.
Yes, I think we are alluding later to that. I mean, for example, I mean, we had this example. I mean, we had this all equal example, which had an equal constraint. Of course, we could, if I understand the question correctly, then we could do something like all equal prime, where we don't have this. But instead of the constraint, we provide the function as an argument. I mean, the comparison of A's. And then okay, then I have this extra argument here. Let's call it EQ. And then instead of, then here I could use EQ. And I must pass in the same comparison, it's prime. Right, so in that sense, yes. I mean, we could always instead, and there's actually a slide for that later, sometimes even in the prelude or in the standard library, there are like two versions of a function. For example, for sorting a list, there's one version where it just has an odd constraint. So, and there's a version where you can give an explicit comparison to sort like in a custom order. So yes, you can always, I think, at least for Haskell 98, I mean, for like more complicated, I mean, there are certain things you can do with type classes, like different things, like associated types. Then maybe not, but like Haskell 98, basic Haskell, I think you could always remove the constraints and explicitly pass in the functions you need, the methods you need. Okay, other questions?
Yeah.
Yes? Sorry? No?
Okay, so like the same person asked a question, meant another thing. Can you just define the functions without using type classes? I mean, you know, like
Yeah, but then
to choose a type, right?
But then you would need to choose a type, and then it wouldn't be polymorphic. I mean, I can of course define something like an eq-bool and then use that, but then it would only work for bools.
And then if I use that function, that in another function, I can only use bool in the other function. So then I'm restricted to bools, and everything that depends on that, I need to like recreate the same like 100 functions that we ever need in all the types that I need. So this way, you just reduce your code a lot because it's just a single constraint that works for every type.
Exactly. Right. Okay, that's odd. Any more questions to odd? Okay, so as I said, so this is a new thing we hadn't seen before. So let's call this super class. So I mean, the terminology is that it's a super class of odd. So you can also have more than one super class when it's so that, as I already verbally explained, you can't give an instance of odd without providing instance of eq. And also conversely, if you have an odd constraint, then the compiler knows that you also have eq. So that means if you, for example, in this all equal here, I could change this constraint to odd, and it would still compile, even though I'm using equals equals, which is not a part of the odd class. But the compiler knows odd is eq is a superclass of odd. So because of this constraint, I in particular have eq. So it can figure that out. Right. So I wouldn't need something like this because odd already implies eq. So I can leave the eq out. So show we have already seen, but not in its full glory. So in addition to the show method that is very simple, takes an A and produces a human readable string, there are actually two more methods in. One is show sprec and one is show list. And they are used, so show list is to do optimizations for lists. And that, for example, I don't know how often that is used, but the one point where it's used is for the show instance of characters. Because if you have a list of booleans, for example, and if you do, I mean, if you show it, then the way that list is shown is with angular brackets and then showing the elements separated by comma. But if I show the list of characters, A, B, C, then, sorry, not show, I mean, this is double now. Then it doesn't do it like this. So then it doesn't show angular brackets and the A, B, C separated by comma. It instead uses double quotes and the characters without single quotes. So that's, I think, because the show instance for characters makes use of this show list. So it doesn't use the default implementation, it uses something special so that strings are displayed in a special way. But you can, I mean, I've never used it myself. And it shows sprec, that is if you want to get precedence right. So that takes an argument that the precedence level you are at. So I mean, for example, if you think of these arithmetic expressions we had yesterday with plus and multiplication, maybe you want to use the usual rules that multiplication binds higher than addition. So then something like 3 plus 4 would be displayed differently whether there's a multiplication somewhere or not. Because sometimes you need parentheses and sometimes you don't. And this show sprec is used to enable you to do things like that. But that's relative, I mean, it's not often, I mean, normally one just uses the automatic derivation of the show instance and you don't have to bother. So it's enough to implement show, but it's also enough to implement show sprec. So then show is, so both have a default implementation in terms of each other, but you need to implement one of the two. Right. And as we already saw on the first day or so, in GHCI, in the REPL, if you ask the REPL to evaluate an expression, then it complains if the result type doesn't have a show instance. Then, I mean, first we didn't have a show instance for our blockchains, and then we got an error message when we wanted to display one. So that has like a special use in the REPL. Okay. Yes, and we saw that error message. So it's not a programming error, it's just a thing in the REPL. Right, then there is something we haven't seen yet, or at least not, I think not, or maybe briefly, that you also almost never implement by hand. Yes?
What does show sprec mean?
Show precedence. So it takes this additional precedence argument. I don't think, do I have a good example? Yeah, let's see. For example, our tree type. Let me just repeat that. Data, what was it called? Just tree. It was leaf A and node tree A. And let's derive a show instance. Okay, and I'm not sure, I hope this works. So let's, I mean, if we just have a leaf X, it's displayed like this. But if I have node there are parentheses around the leaf X and leaf Y. And
maybe if you use multiplication plus something like that.
Yeah, but that's an int.
Yeah.
I needed some, let's see. And first of all, of course, in order to try this, I mean, hang on. Show spec. First of all, it takes an int and an a, but it doesn't give you a string, it gives you a show s. So first we need to understand what that is. So let's ask for information on show s, and that's a type synonym for a function from string to string. So I think it takes like the given string and appends or prepends the given string. So we can first try this out. Shows prec whatever 0 leaf x, and now just okay, fine. First use that. Okay, so the given string is appended. So you basically get show back if you use the empty string. Okay, now I can hope that if I do something else here that at some point it will change. I'm not sure though. Maybe I'm wrong.
Maybe you need a node.
Yeah. See? So because I think function application has precedence 10. So that means it's printed without parentheses if the precedence is lower than 10, but from starting at 11 suddenly it has parentheses. And this is then used to do what I had earlier. I mean, the show of node is then implemented in terms of that. So in order, I mean, if you look at the implementation, and we can't because it's automatically derived, we can't look at the implementation. But if we could look at the implementation, then in the case for node, it would make use of show spec for the children and give an appropriate precedence level so that the children know whether they need parentheses or not. So that's what that is used for. But as I said, you normally never have to worry about that.
Maybe if you remove the parentheses in leaf 1, you will add them when you print. If you remove the parentheses there.
Which ones?
In the last leaf 1.
Oh yeah, sure, it will add them. I mean, it's the same expression.
But that's what it does.
Yes, so that allows you stuff like that. I mean, show shouldn't always result in the same string because it can depend on context. If you need parentheses, I mean, normally it's used for parentheses. So sometimes you need them, sometimes you don't, and this show spec allows you to do that correctly. But as I said, you normally never have to worry because you always derive show and then it just gets it right automatically. So I have done that very rarely because it's a bit complicated. But yeah, that's what this show spec is for. So that's used under the hood for this automatic derived things. But I mean, in practice, you almost never use that directly. You just use show. And it's just used in the implementation of show for like complicated types to get the parentheses right. Does that make sense? Okay. So read is the opposite, sort of. And I don't even know what, okay, fine. But one basically never uses that directly. I mean, so opposite in the sense, I mean, show is used to take some Haskell value of some type and produce a human readable string, and read is for the opposite. You have a string and want to pass it into a value. And ideally, I mean, normally, even though the compiler doesn't enforce that, it should have this round trip property, right? If you first show something and then read it back, you should end up with the same thing. And you should also be able to read everything back that you show. But that's not guaranteed, and there are also exceptions. But I mean, that's the general idea. It's a bit like pickle in Python, except that it's like human readable and not binary. And those I've never used in my life, these read spec and read lists. So if you want to pass something, then you always use read. So we can try that out. And the only complication here is that the A is only mentioned in the result type. So especially in the REPL, the compiler, you must somehow tell the compiler what type you want to apply that on. So we can try this out. For example, read the string true, and then we must tell the compiler what we want. So in this case, a Boolean, and then it will successfully pass the string true as the Boolean true. And if it can't pass it because it's whatever, then I get an exception prelude read no pass. So that's like a simple, quick and dirty way to pass values, Haskell values. And we can also use it with numbers, for example. Yeah, so that's read. And you can also automatically derive that. So I could add that to my custom types, the read.
I put the type wrong.
The type wrong? Oh yeah, then if you put the type wrong, then you get the same error. If I want to pass 1, 2, 3 as a Boolean, then it's also no pass. Okay. And sometimes you don't need this type annotation if the compiler figured it out from context. So for example, here I had this here. I had to tell it that I want a bool, because otherwise how must the compiler know that I want to turn the string into a bool and not into an integer or a tree? But if I do something like this, then it works automatically because it has enough context. It knows what, because logical OR takes 2 booleans, so it can infer that the first argument must also be a boolean. So therefore I don't need a type annotation there. So normally when you, if it's in a module, if it's in a file, if you write Haskell, you don't need the type annotations, because then after you have passed something with read, you will use it, and then from the context how you use it, the compiler normally might figure out the type. But like in the GHDI, you normally need more type annotations, because there's less context for the compiler. Right. Okay, and then we can do this strange thing. What's that? Right, and this, if I try that, then I get an error message, ambiguous type variable A0 arising from use of read. So the problem here is, read is polymorphic with result type A, and show is polymorphic with an with an argument type A. But the compiler has no way to figure out which A I want to use here. So it internally calls this A0, but then can't nail it down, because there is no context that tells. All it knows is that this A must be readable and showable, but it doesn't know which A. And there are many types that are readable and showable. So if I want to fix that, I can, for example, give a type annotation. So for example, I could use it for int. And now it should compile. This actually the signature I can provide to make the warning go away. And now I can use it. So strange 42. So now it passes the 42 as an int and then shows it again. But now I could do it with bool. Of of course. Right. But now, of course, if I say it's a Boolean, it won't work for 42 anymore. Now I get no pass, because now it tries to pass this string as a Boolean, and it isn't. It can't. Okay, so I explained what the problem is. And this is one fix, and this is another fix with bool. But the choice, what I write there, makes a difference. So in the one case, the string true works. In the other case, the string 42 works, but it depends on what I write there. So it makes a difference what this type is that is invisible if I don't explicitly annotate it. Questions? Right. So yeah, if that happens, I mean, there's an example that actually does happen in practice sometimes. So you have like several polymorphic types, and you combine them, and in a way that it's not obvious anymore which intermediate types you're using, then you need an explicit annotation like here. Right, and that we already, I think I mentioned that in the first lecture already. So for some types, like those four that we just saw, eq, ord, show, read, you can just use a deriving clause. So after you have defined your data type, you can say deriving, show, read, eq, ord, and then if it's possible, then it automatically generates this for you. So for example, for my for my tree, I mean, we already did it for show, but I can also add read, eq, and ord, and that will work. And there are a couple of more. But this is, I think, part of the Haskell 98 standard. So every compiler that, not just GHD, would allow this. And then there are a couple of classes that we will look at later in later lectures, where GHD can automatically derive it, but that's not like part of Haskell itself. That's a GHD extension. But I mean, most classes, I mean, or a priori, you can't do it automatically. Then you really have to write an instance. Although these days, I think for most classes that float around on Hackage and libraries, there's always some way. I mean, there are also other ways to do that automatically that we might talk about towards the end of the course, namely generic programming and template Haskell. So in most cases, you don't really have to do it yourself. There's normally an easy way. But I mean, a priori for a given class, you have to write an instance by hand. There are only like these exceptions where you don't have to do it. And I mean, if you can derive it, you normally should, because this automatic deriving mechanism ensures certain consistencies. So for example, that show and read are compatible with each other. So if you derive it, you can be reasonably sure that it has this round trip property. If you show something, you can then pass it back into the same value. And also that eq and ord, for example, are compatible, that if the compare operator returns eq, then the equality operator would also say they are equal. I mean, if you do it by hand, you must make sure by hand that these conditions hold. Okay. Okay, that's exactly the example I already had. And I mean, we can try it out, this eq for some, I mean, we had this tree, sample tree, this one, and if I do read, of this string, and tell it it's supposed to be a tree characters, then it can successfully read it back into the Haskell value. Yes, so that's that. Oh yeah, and equality is also as one would expect. So for two trees to be equal, I mean, they must have the same shape, and then for all the leaves must be equal. And ordering is, I mean, it's also in some sense lexicographical, but I mean, whatever that means for trees. But sometimes it also doesn't matter what it means. I mean, there are some, as we will see in like later this week maybe, I mean, there are some data type like Haskell. I mean, we had this lookup table as an example yesterday, but that's very inefficient because in order to look for an element, you always have to start, I mean, linear search from the list. So if you have many key values, then it's inefficient. And there's like a very commonly used library on Hackett called containers that provides a map type that basically has this interface that we implemented with our lookup table yesterday, but it's implemented as a binary search tree and balanced binary search tree. And in order for that to work, you need that your keys have an OR constraint. Yesterday, we only needed an E constraint for our implementation. So what I'm wanting to say is that sometimes it's useful to have an OR constraint even if you never really want to compare. I mean, like probably you never want to say this tree is larger or smaller than another tree. Nevertheless, it's always useful to have an OR constraint because then you can use trees as keys in maps. So I normally derive whatever I can derive, even if I'm not needing it, just in case. And also we saw earlier that, I mean, for example, this second example we did for eq with lists, that automatically you have equality for lists if you have equality for the elements. And there are many, many cases like that, where you, given certain constraints, you get other things. And for example, if you write a web server or whatever, and you have your custom Haskell types all over the place, and then you want to write endpoints, and you want to like as input, you want values of your Haskell types, then you use something like ASON that I mentioned earlier, this JSON parsing thing, and you want to be able to that the users can use a JSON request body, and then you pass it into your Haskell types. And that normally works beautifully, and you don't have to write a single line of code to get this JSON serialization, but only if all the ingredients of your types have JSON parsing. So if there's, your types use other types, which use other types, which use other types, and if there in this chain there's one that doesn't support JSON parsing, then the whole thing also doesn't. And that sometimes happens if you're lazy in the beginning and don't think of that, then in the end you can't easily serialized because somewhere some stupid little type doesn't support this. And therefore, as a general rule, I always try to at least those 4 to derive them for all the types I define, because then you have less problems down the road. Okay. So numbers, next topic for a question. Yeah?
How is deriving and typing files, are they related in any way?
Don't think so, not directly. Both use the compiler, but
Yeah, those, like the algorithms to create this deriving are already like hard-coded in the compiler. I'm not sure if it relies too much, but the properties of Haskell of being like this strong system, this strong type system, and the purity and all this makes for a really easy code generation mechanism. So it gives you like and having these constraints makes it easy to generate code. So these mechanisms that are repetitive in Haskell are abstracted away every time. So you get a lot of these kind of mechanisms to avoid writing code.
Okay, numbers. We already had some examples. We mostly used int and also double once or twice. And there's like this, I think it's called the numeric hierarchy. So there are a bunch of type classes in Haskell in the prelude that are related to numeric types. So the most general one is called num, And all the, basically that's what it means to be a numeric type, to be an instance of num. I mean, we can, right. And then there are various others. So integral for integral data types like int and word and so on. And then this fractional for like non-integral ones where you can have division. And then there are others like floating and real frac, and I can never remember which is which and what they do. But yeah, it's quite complicated. And I mean, we can look at this. So let's just look at this. So if we ask for information on the num class, so it has plus, minus, multiplication, negation, absolute value, signum, and a function from integer. And integer we haven't seen yet, so integer is arbitrary precision integers. So they can be, whereas int is 64-bit integers. And basically you need everything. And there are, right now these implementations in scope: word, integer, int, float, and double. But there are many more even in the standard libraries. So there are versions of int and word for like 16 and 32 bits. And 8, I think, word 8, bytes you also have, and int 8, I suppose, signed bytes. And then, so even in the standard libraries, there is a bunch more. I think complex these days also in the standard libraries. And then there are, of course, also libraries on Hackage, third-party libraries that have their own num types. So there's a whole zoo of numeric types. And if we, for example, look at integral, we first of all see, is integral is a good idea? But it was bad because, what?
Maybe enum first.
And why doesn't it have to be num? Oh, real, and real has to be num. Yeah, so okay, let's look at enum first. Right, so enum is for types that basically are like well ordered step by step. So in particular it has this, you see it has this to enum and from enum is minimal. So if you implement those two, everything else you have. And to enum and from enum is int to a and a to int. So it's basically, typical example is character. So character is so for example, you have to enum x, from enum 120, and I believe that's the ASCII code of x, of small x. Yeah, but that in that range it's the same as ASCII.
Oh, yeah.
But of course characters can be UTF-8, Unicode. So I can have a German SZ, and that's then outside of the ASCII range. And the opposite also works, so to enum 121 of type character. Y. Sorry, it's a number. Is y. So that's enum. I think, but bool probably is also an instance of enum, I'm not sure.
Yeah, I think false is first.
To enum, let's try it. 0. False, and 1 is true. Okay. So yeah, all where they are like neatly ordered values in a row that they can map to and from int, that's enum. Sorry. So that was that. So enum. And you see there's things like suc and pred for successor and predecessor that you then automatically have with enum. So for example, I can say the successor of x is y, and the predecessor of capital Q is P. Right, so that's enum. And what was the other one? Real. So let's look at real. So real in turn has as superclasses num and ord, and additionally two rational functions. So rational is another numeric class that was not on the slide. That's arbitrary precision rational numbers. So for example, and they are displayed, I think, with a percentage sign as the fraction. So I can do whatever, 2 rational, 2 int, and it's 2 over 1. And that's arbitrary precision. So both the numerator and the denominator can be integers. So they can have arbitrarily many digits. So
Do we want to talk about the special syntax for infinite list with because of the enum?
Is that only depending on the enum?
Yeah.
Right. Right. Yes, we should. Thank you. So enum, I mean, this is that, and I mean, normally you don't never need that. I mean, sometimes I need it for characters when I want to check whether, I don't know. Sometimes if you want like don't forget that. You don't really need it ever. But what you do need it for is there's a special syntax for lists. You can do something. I mean, if
you can use that if you are checking if your password contains all the lowercase characters, for example.
Yeah, but you could also just do that with A and Z. I mean, instead of using 2 enum and the ASCII range, you could. Yeah. I mean, for example, if you want the list of ints from 1 to 100, then you don't have to write it like this and going on. There's like a special syntax in Haskell. I must just tell it, I mean, because it doesn't know now this is int. I mean, it could be another numeric type. I can use this ... And I could do the same for characters. So I could say whatever, C ... Y. And I get the list of characters starting at C, D, E, F until Y. So this ... And that only works if the element type is an instance of enum. So the special syntax with the ... works for innumerable types. And there is a variation. If I want only the odd numbers from 1 to 100, for example, I can do 1, 3, ... 100. So I can give the first 2 elements and then ... and then it keeps that, I mean, the arithmetic sequence, so it keeps the same distance between subsequent elements. Yes, so that's basically the main use for this enum class, that you have this syntactic sugar. And actually you can even leave the 100, then you get an infinite list. So I can say odds equals 1, 3, ... no upper bound. So now odds is an infinitely long list of odd numbers, all not I mean, okay, it's int, not integer, so it stops, I mean, because it's only 64-bit, but very long. So maybe I should make it really infinite. So now it's really an infinite list of all the odd numbers. Of course, if I now did this and press enter, then it won't stop, but I mean, I can. So it just goes on forever. Right, so that's this ... and enum. Right, so now we were at real. So real is numbers that can be ordered and that you can convert to a rational number. And then in combination, we saw if it's enum and real, then it's integral. But it also had like additional stuff. So it must be real and enum, and as you can see with the minimal quadrem, so quadrem is, it must have like integer division, so you can divide with the rest, so you get a rest, and it must be able, you must be able to convert it to an arbitrary precision integer. And then you have these things, quad and rem and diff and mod, and I mean, so basically the point of integral is that you have this division with rest. So for example, we can, I don't know, divide, I mean, we can do quad or diff mod. I mean, the difference between diff mod and quad rem is just with negative numbers. You always, it's, I don't know whether we should go into that. I mean, for a mathematician, I think the diff mod makes more sense, and for other people, the other thing. Let's take 24 and 7. Let's use int. So, it's a stupid example. It's a 5. 10. Okay. So that means 24 divided by 10 is 2 with the rest of 4. And the difference is just if I have a negative number, then for diff mod, so let's do this. Okay, so if it's positive, then diff mod and quad rem are the same. But if it's negative, then you see, I mean, it's not clear. I mean, diff mod gives me, okay, minus 24 is minus 3 times 10 plus 6. And quad rem says minus 24 is minus 2 times 10 minus 4. So diff mod, the rest is always non-negative. And with quad rem, it's always the same sign. Exactly. But anyway. But yeah, so that's integral. And what else do we have then? So that's the one zoo of things, the integral one. So integers, ints, words, 64-bit words, 32-bit words, 16-bit words, and so on. They are all integral. And then we have the floating point stuff. So, or not necessarily floating pointing, the fractional ones. So rational is fractional. So for example, I can divide 2. The rational 2 divided by 3, and it gives me 2/3. So it's precise. It's not. It doesn't round or. But then I have doubles. Let's see what was on this slide. So float and double, for example. So it in particular has fractional, and then those also have, like, rational is only fractional. So let's look at fractional first. And I mean, you don't have to remember all of that. I also always forget this. I mean, just enough to be aware that there is this huge hierarchy of numeric classes and all sorts of operations. So fractional is simple, so it must be a num. And minimal, and here we also see an example of a bit more complicated minimal thing. So this says you can either implement from rational or the combination of recip, No, you always have to implement, it says you always have to implement from rational and then either reciprocal or division. And basically, so fractional allows you to divide 2 of the numbers. So it's different to integer division where you have the rest. So here it's like you divide without rest. And this recip is just a reciprocal. So if I ask for recip 1 of type double, should get a third, not 1, 3. 3, then I get 0.3333. Or I can divide doubles. I mean, I can, for example, divide 2 by 3 and I get 0.66666. So that's fractional. And then what else do we have? We have floating and real frac. So I always forget what that is. At first, I think real frac is simpler, actually. Yes? No? Okay, so real frac, it needs to be real and fractional, so the name is sort of suggestive. And what does it do in addition to that? So you can do rounding stuff. So if you, for example, truncate. So if you have some integral type, then you can truncate into this integral type, or you can round. So, I mean, for example, we had for double is real frac. So if you have whatever, 30, we can say round 36.8, and we want an int. And I have to tell it that this is a double. Then we get 37. So that's this real frac thing that you can round and truncate and floor and ceiling and those things into an integral type. And finally, floating. is all the like transcendent stuff. So it has pi, it has the exponential function, logarithm, square root, powers, sine, trigonometric functions, the hyperbolic functions, and other stuff that I have no idea what that does. Right, so I mean these things is then for double and float are the typical ones that implement that, and maybe complex numbers as well. Yeah, so there's this whole zoo of but I mean don't worry too much about it.
You can always use colon I or Euclid and
Exactly, don't have to learn all of that. So, right, I already said most of that, I think. So int is bounded 64-bit. I think that's not guaranteed though. That I mean, nowadays it's 64-bit, but
if your computer is 64.
yeah, it's like.
Yeah.
But I think like 20 years ago it might have been 32-bit. So it's not in the standard that it has to be 64, I think. But anyway, an integer is unbounded. And double is normally of higher precision than float. Rational is, as I said, like proper fractions without rounding. Okay, we have the operations. And now what is interesting if you ask for literals. I mean, I did that before. So if I ask for the type of 5, for example, then it doesn't say int or whatever. It says for every numeric type, 5 is of that type. So this, so that means, for example, if I want a double, I mean 5 as a double, I can just do this. So these literals without a decimal point, they are numeric literals for every numeric type. And they are implemented with, if you recall what the num type was, there's this from integer function. So what actually happens under the hood is the literal, in my case the 5, is passed as an integer. And then the from integer function is used to convert it to the type I want. So that's how that works. And then there are also literals with a decimal point. So if we ask for the type of 3.7 type, then there's a different constraint. So then it must be a fractional A. So I can't use 3.7 if I want an int, but I could use it to want a rational or a double. So for example, I could say 3.7 of point double. I mean, this looks unsurprising, but I can also say 3.7 of type rational, and then hopefully, then it says that's 37/10. So it's, so that's numeric literals. And then, I mean, I showed you those things, most of them. Right, so there is no, I mean, I don't know in which languages, like in many languages, there is automatic coercion between numeric types, but not in Haskell. So if I have, whatever, a double, 3.5, type double, I can't add an integer to it. That gives a type error. So in this case, what I would need to do is, for example, use this from integral. There's a function from integral that can convert any from, this would work in this case. Right. So that is one thing that's like unusual in Haskell, I think. In most other languages, there's like implicit conversion between numeric types. If you have an int and want to add it to a double, it gets automatically converted to a double, not in Haskell. You always have to do that explicitly.
That also because you can define your own numeric types. So in most programming languages, that's hard-coded into the language.
Mm-hmm. Yes, we could define a new numeric type. And if we write a proper instance of num, then these numeric literals, like 5, would also work for our own type. Don't know. Yes?
But we only do 3.5 plus 2 directly.
If we do that, yes, we can do. But then, because, I mean, 3.5 had this constraint fractional. 2 has the constraint num. but fractional has num as a superclass. So both have, yes, so we know that, I mean, that works as long as the 2 is also in the same fractional type. So this works for an arbitrary fractional type. So I could now do this. So I could say double, and I would get my 5.5. I could say rational, and I get 11 divided by 2.
So you get the inference goes to the most constrained type.
Mm-hmm.
That's it.
Yes, the 2 could be any numeric type, but the 3.5 must be a fractional type, so the whole thing must be a fractional type. Right, and often one needs these conversion functions. So one useful one is this from integral. There's also to integral, and from integer and to integer, and from rational and to rational, I think. And with those, normally you can get that right. So I mean, that happens often that one has like doubles, but also integers, and someone wants to mix them, and then using from integral normally fixes that. So Haskell is very explicit about it. So no implicit conversions happening. It's all one specific type. Okay, can you answer that question? I think we already basically answered that.
Yeah.
Although
The diff creates a new constraint, a more fixed constraint that doesn't overlap with 3.2.
but what was this? Times 2? Okay, that's the same as what we had in our example. And this is also fine. I don't really understand the example. I think what he means is in the REPL, because then it uses the default.
Yeah, it does. Yeah.
I mean, this would be... Oh yeah, but the problem is there is no thing that's both fractional and integral. I mean, there's no type, at least none of the standard numeric types has both. So it's either fractional or it's integral.
So if you remove the type, it should not work, correct?
Yes, yeah. Yeah, because it doesn't, I mean, if I had a numeric type that does have these constraints, it would be fine. But that is like opposite things. Either it is like a continuous type with fractions, or it's an integral type, but normally not both. Anyway, no need to dwell on that. Right, this I mentioned from integral. So this has a very like generic type. So it takes an arbitrary integral type A and an arbitrary numeric type B, and it can always convert the A to a B. And the way that works is, if you remember, the integral type had to integer, and the numeric types have from integer. So this is how this is implemented, the from integral. And then, I mean, we saw the round floor ceiling things. Okay. So that was, I think, that on numeric types. Let me just quickly check how much there's left. Oh yeah. So this we can definitely do, and then there's, but most of that we have done already, so we're almost through. Okay, so what have we, yeah, question?
So now when you come to blockchain, now something like Solidity and the EVM,
Mm-hmm.
I think the last time I was learning, there's something that the EVM is not compatible with decimal places. But now in Cardano, can you work with decimal places?
I mean, the Plutus has, in principle, uses integer under the hood, so arbitrary precision integers. And rationals. You can use rationals in Plutus. So you have like arbitrary precision. Yeah, I mean, yes, you could have.
Decimal places.
Yes, I mean, it doesn't. I mean, Plutus itself, Plutus core doesn't have a, like a double or something like. But I mean, if you have fractions, then you can, of course, do that. I mean, you can have arbitrarily many decimal places for your things.
Like the the end developer can use them, but then it gets translated to a fixed non-floating point type.
Yes, rational. Bluetooth, I mean, uses integer and rational. Yes, so in Bluetooth you don't have to worry about overflows and decimals and rounding errors and so on. But of course, at some point you want to like interface with the user, and you don't want the user to enter fractions. So somewhere you must round. But I mean, Bluetooth itself has like arbitrary precision. But of course, also you have to pay for it. I mean, in Bluetooth you pay for the size of expressions and the runtime. And of course, if you have huge denominators, then that makes the transaction bigger and more expensive. But in principle, yes, it has arbitrary. Okay, so what have you seen? So there are like built-in types like int and char, even though I think int is not really built in, but whatever. But like very fundamental.
There's the int, the primitive int, and then this.
Yeah, there's a primitive int, but never. We get to that later. So there are like built-in types that are really like hard-coded into the compiler. And then there are that we could have defined ourselves, but don't have to define because they are in the prelude or the standard libraries. That's things like, So the most weird ones or most fundamental ones are the built-in ones, like character and int. Then we have some like lists and tuples that we could have defined ourselves, but they have special syntax. So in the case of lists, we saw that we don't have to use the constructor and you don't have to write 1:2:3 empty list. We can write it nicely in square brackets. And for pairs, we have seen that there is not a constructor called pair or whatever and takes 2 arguments. We have these parentheses with the comma. So there's special syntax, but that's just syntactic sugar. So in principle, you could have defined those types yourself. And then there are types that are just, defined in the library. So there's no special support from the compiler, syntactic or otherwise. So the bool may be either. So they are just definitions in the library. And finally, there are also types that are just synonyms for other types. So string is a synonym for a list of characters in Haskell. Right. And then, of course, you can also define your own types, as we have seen with the tree type or those. Right, and as I demonstrated a lot today, this :I is very useful to get information about a type or a type class. So in the case of type class, you see, the definition and what you need to implement if you want to write an instance of the class, and also the known instances. And for type, you for example, for data, you see maybe that's interesting, we haven't done that yet. We did something like :I eq, and then we saw all the instances. But you can also do, for example, :I bool, and then you do see the definition. So bool has the constructors false and true, but you also see what classes bool is an instance of, which is also useful. Bounded is, I think, the only one on the list we haven't talked about yet. So maybe I should briefly mention that because that's quite simple. So bounded has just 2 methods, min bound and max bound. So that's for types that have a smallest and the largest element. So for example, we can ask for min bound of int, and we get a large but finite number, and we can ask for max bound of int. So this will be 2 to the 63 plus minus 1 somehow. Yeah. Right, and you could do the same for integer you can't because that isn't bounded, but I'm actually curious what happens if I do it for character. Not very enlightening. Okay. Yes. Yes, I can do that from enum. Okay. Oh well. So it's 1,114,111 Unicode characters. Okay, so yeah, that's the bounded class. That's also sometimes useful if, for example, you want to, yeah, I don't know, sometimes useful. I mean, for example, you could do, I mean, if you wanted all orderings, then you could do min bound, max bound, ordering. No, it's a list of orderings. Right, and then you get them. So for that, of course, it must be an instance of both bounded and enum. Sorry, yeah, we were there. But where was I? I was at bool. Right, so we see if we do :I for type, we get all sorts of nice information. The definition of the type and the instances of it. And now we have seen all of these classes already. Eq, ord, enum, show, bounded, read. There could be more, but I think it only displays the ones that are in scope. So if in some library there's some other instance for bool, of course it wouldn't show here. Okay. I'm not really sure what the partial means. But anyway. And you also can do that with functions, for example. So I could ask for I sign, and then it shows me in this case that sign is a method of the floating class and has the signature A to A. Or, I mean, yes. Or, I mean, I had this toUpper, I can ask for information of toUpper. And there it's simple because it's not a method of some class, it just says toUpper is a function from character to character. So, I mean, these days, I mean, you are spoiled, or you get spoiled, because in VS Code it's very nice with the mouse, you immediately get information. But in previous iterations of this class, especially the first ones, there was none of that. And if you wanted to see something, information about something, I mean, you all the time had to use :I and :T, because it wasn't just that you hover with the mouse and then something pops up. That's quite recent in Haskell. That was one of the big pain points with Haskell, that the editor's integration wasn't good or not existent. So he basically wrote in some dumb editor, text editor. So this IDE support with Visual Studio, that's not old, maybe 2 or 3 years. Yeah. So that was even more useful, because these days I think I basically get this same result if I just hover. So if I just hover here over the bool, okay,
documentation is source.
Yes, so I can, okay, fine. Don't know whether that works. Not really. But I mean, I get like type information by just hovering of show. Yes. So, I mean, but that, as I said, that's very recent. So in the old days, you didn't get that. Okay. Oh, there it is. I was just too impatient. So clicking on that, and it opens the documentation on Hackage of bool. Speaking of Hackage, I forgot, Robertino told me. So I wanted to show you Hackage, I did that in the beginning. But I also wanted to show you Hoogle. So there's something called hoogle.haskell.org, hoogle.haskell.org. And there you can search basically most common libraries on Hackage. So you don't even need to know where it is. I mean, for example, we could do sign again, and then it.
It's in all those libraries.
In all those libraries, there's a sign. So it's not just this is the one from base that we looked at, but it seems there are also other libraries.
Numeric prelude.
Yes, that define their own version of sign.
And you can also put, if you know that you need a function that takes a certain type and returns a certain type, and you know that it exists, you can just put the type, and it will give you all the functions that apply to a type.
Do I need the constraints as well?
like
I mean, for example, if I want to sort a list, and I don't know whether there's a list sort function somewhere in the standard library, but obviously in order to sort a list, it must, I mean, list of A's, so I want to sort a list of A's. So obviously, as a result, I want the sorted list. And obviously, this can only possibly work if I have an OR constraint on A. And I get, I'm told that there's, for example, a sort function with exactly the signature in the base libraries. So that should be available without me doing anything, importing anything. So I should be able to sort Kenya out. Yeah. No, okay. It's in the base library. It's in base, but not in Prelude.
data.list.
So I must import data.list, and then it sorts it. Right. Yeah, that's useful as well. So that's Google, especially for beginners. If you don't have a good overview yet, what exists and what doesn't, Google is useful to find functions, suitable functions. And you see there are lots and lots with the signature from all sorts of stuff. Anyway, right. Yeah. So sometimes this colon I can be confusing. That's what the last remark there is. Because we see that int is not really built in. Instead, it's another data definition, but it's very scary. But anyway. So that happens sometimes, unfortunately. So in particular for beginners, that you do something seemingly innocent and then you get some horrifyingly complex answer. So don't worry about that. Right, this I think is not what's there. I think we have covered all of that already.
Yeah.
Except maybe, so we can just quickly go through the slides. So I mentioned that already in the first lecture or the second, that higher order function is a function that either takes another function as an argument or returns another function as a result. So we saw examples, we did see examples of that, like filter or map, that take a predicate or function and then apply that function to each element of the list. We also talked about currying right in the beginning, and that strictly speaking, something like lm is also a higher order function, because I mean the signature is written as a to list of a to bool, but I told you that I mean this arrow is right associative, so strictly speaking that Haskell doesn't have functions with more than one parameter, so everything has one parameter. So strictly speaking, functions like that are also higher order functions, because if you plug in an a, you get a function from list of a to bools. But this is normally not meant when we talk about higher order function, even though with this definition it would be one. But true higher order functions are like filter and map that we saw, because they really take a function as a first, I mean in this case first argument, doesn't have to be the first one. And yeah, and right, so filter, and one could also see that as a function. I mean, if we use the right associativity of arrow again, you see that as a function that takes a function and returns a function. But that's maybe a bit weird, but nevertheless. And this is something that actually somebody asked already when we talked about all equals, whether one can do that without class constraints. So this is just overloading versus parameterization. So I just showed you this sort function. So given you can order the elements, then you can sort a list. So there's this version that we just used as an example, but there's another version that doesn't have the OR A constraint, but instead explicitly gets a comparison function. Right. So, and then of course it depends. I mean, if you want the standard ordering, then you would use sort, so that's easier to use and I mean, less verbose. But sometimes you have like a special ordering that you need, like for example descending instead of ascending, and then you could use the sort by function, because otherwise you would need to define a new type with a new odd instance in order to use that, which you don't want to do. So it's similar, but the difference is that the first one has this constraint and the second one has explicitly this ordering function. So the one is more convenient and the other one is more flexible because you can sort in different ways. And actually, interestingly, the actual underlying implementation, how GHG implements type classes on constraints, is that it in principle does this. I mean, we saw that in the ORD class that you could just implement compare. So basically, an ORD instance is just an implementation of the compare function, which has this signature A2A2 ordering. So under the hood, what GHG does is it passes these double arrow constraints around as so-called dictionaries, where for each method, it's like a record, for each method you have the implementation. So there's like hidden implicit parameter arguments that look like this. So under the hood, sort is basically implemented like this, like sort by. So in that sense, this double arrow is really very similar to a single arrow. I mean, because, I mean, in its intermediate representation that we might talk about later, there are no type classes anymore. So type classes are implemented by passing extra arguments around that say how to do these things, like comparing. Right. Performance. So parametric polymorphism that we talked in the beginning of today has no overhead in cost. Whereas this ad hoc polymorphism with type classes does get, as I just said, some additional argument at runtime. So there's a little overhead for that. But there are also ways, if you're really that worried about performance, to give special flags that tell GHG to optimize that away, basically, and it creates special versions of your functions that are specialized for certain types, where all of these things are already like implicit. And there's also an aggressive inliner. So GHG, I mean, we brushed on that in the first lecture, that because of purity and these guarantees that the compiler has that you don't get in other languages, the compiler can do very aggressive optimizations and be sure that they are correct. So it can remove a lot of overhead automatically, especially if you activate optimization in the compiler, I think. Right, and just to recall, so we looked at two versions of polymorphism. So one is this parametric polymorphism, where you can use the same implementation for all possible types or many different types. And it's completely unrestricted, and the caller decides for which type to use it. And then we looked at type classes, so-called overloading, where you can use the same name of a function with different implementation for different types. And we also saw examples that it's not, I mean, even like interfaces in C# or something, they have something that looks a lot like type classes, but normally the signatures are quite restricted. They can only appear on the left-hand side as inputs, for example. But we saw with read, I mean, there the signature of read was string to A. So in Haskell, it can also appear like on the right-hand side. Also function arguments and result types. And you can use them to define a common interface in terms of just common functionality in terms of just a small interface. So for example, once you have compare, you can implement all these other things like less than, greater than, and so on. I think that's it for today. I'm not sure what's the plan now with, I mean, we could talk about some of the exercises if you still want to go on. I mean, the lecture is done.
So, in the first day and the second day, we publish the exercises for that, so you should already maybe started. This lecture, we don't have exercises because we feel like with the two previous ones there's enough to cover. And on top of that, we're going to still be here. So if you want to start working on the exercises by yourself and with our support, or if you want us to go over some of the exercises and explain like the reasoning, so that if that will be more helpful, your choice.
Yes, so we can do both. But in any case, we should probably have a short break first.
Okay. Well, a short.
And then,
How long?
yeah, I don't know, the catering is probably not there yet, is it?
No.
Okay, then just 10 minutes,
10
and
minutes.
then you can think what you want to do. If you want to work on the exercises or go home, or if you want me to show some examples or something like that. Okay?
Okay.
But in any case, let's have a short break. actually this is like this. So you can also see it as a function that takes an A and returns another function of type list of A to bool. And I mean, we can make that explicit. So for example, we can say has y, and we define that as lm y. So we can just only take apply one argument. And now if we ask for the type of has y, it's now from, okay, t characters. You can think of as list. So ignore the t. So list of characters, so string to bool. So I have now provided one argument, the y, and the result is now a function from lists or from strings to bool. And now I can use this. I mean, I can say has y Kenya, and it's true, and has y, I don't know, Haskell, it's false. So this is currying. That basically, in Haskell, a function with two arguments is represented as a function of one argument that returns another function that takes the second argument, and of course it could also be for three arguments. I mean, if I have, for example, let's do another example. I don't know.
Add 3?
What? Yeah, exactly. But I specialize it to, let's say, ints. So add 3, x, y, z is x plus y plus z. So, and I can, of course, use it as expected. So add 3, 1, 2, 3 is 6. So it adds the 3. But I can now consider, for example, whatever I call it, add 3, 1, which is add 3, 1. So I provide the x, but not the y and the z. And this here, I mean, if I do the parenthesizing again, it's actually this. So so that means if I provide one argument, the 1, then what I get is now of type int to int to int. So it now only takes 2 arguments. So now, for example, I can do add 3, 1, whatever, 2, 3, I get 6 again. But if I do 8, 9, I get 18, because 1 plus 8 plus 9 is 18. And I can provide the second parameter. So I can say add 3, I mean, I can name it whatever I want. For example, 17 is add 3, 1, 17. So now the type of this now is int to int. So now I have provided the second argument, so I'm left with a function from int to int. So the x and the y are now always 1 and 17. So if I now do add 3, 1, 17, 5, then I get 23, because 1 plus 17 plus 5 is 23.
Maybe it will be even clearer if we change the inputs to lambda functions, and you make the actual lambda functions match the type. X lambda x, y lambda.
Like this?
No, like individual lambda functions.
Yes. Okay. I mean, normally one would write this. I mean, right. Normally one would write, or one could write this as in lambda notation, like so. But this is just syntactic sugar for the following. It's a function that takes an x and then returns a function that takes a y, and that returns a function that takes a z, and then finally returns x, y, z. So this maybe makes it clearer, yes.
It matches the types?
Yes. So I get x of type int, and I get a function from int to int. If I then plug in a second argument, a y, it gives me a function from int to int. If I then plug in a z, then finally it gives me an int. And that's currying. So I represent functions of multiple, in this case 3 arguments, as basically curried. It's always function with 1 argument. So if I want a function with 3 arguments, in Haskell it's a function of 1 argument that returns a function that takes another argument, that returns a function that takes an argument and then produces the result. And the nice thing is that you can do this partial application like I did here. So if I have 3 arguments, I can only supply 1 or 2 and then use that result. Like I did in this has y. So I can have for example, yeah?
Maybe you can comment this, but apply 3, add 3 to 5, and then like remove the x and replace the x by 5.
Yes, I can do that. So just to see.
That would be the same.
Yes. So just to, for example, if I do add 3, 5, what is that? So it's this thing. Apply to 5. So I must plug in the 5, I must substitute the 5 for x. So that's a function from y to z to 5 plus y plus z. And if I now apply whatever to this, for example 7, then it's what I got there. Sorry, let me just reformat this. If I now supply 7 for y, I get a function, it's this thing here. With 7. So that's the function that takes a z and 5 plus 7 plus z, which is the same as, 7. Which, if I want, I can say it's the same as z 12 plus z. So if I try this, this add 3, 5, 7. This is now function from, this one that adds 12. So for example, if I apply to 0, I get 12. So yeah, that's currying.
So on the inverse and carrying, you're just taking a function,
Right.
multiple arguments, then you're splitting it with the individual arguments.
Yeah, and carrying, like how
Yes.
how can we change a 3 so it's not carrying now with the uncarry function?
Because it's 3, the uncarry function works for 2 arguments. You could write a version for 3, of course. But we could use the lm function. I could, for example, use uncurry.
What's your question exactly?
Oh, okay, just want to visualize the process of carrying and carrying.
Okay.
The step-by-step process.
The curry or the uncurried version of this, basically at 3 prime would be, it would take a triple of a's and return a.
It's
Sorry, I got. Sorry about that. Yes, that would be the uncurried version.
Maybe we could like create an add2, a carry add2, and apply uncarry to it, and show like how it gets transformed to tuples, like actually replace the definition for it.
Not sure I know what you mean, but I could have add 3, 5, for example. That now is a curried function with 2 arguments, and I could uncurry this. And now I get a uncurried function, so it only has 1 argument, which is a pair. And now I could do 100 and 1000. And that will be 1105. Yes. Right, uncurry and curry only are specialized to function with 2 arguments.
Yeah.
Of course, you could write versions for 3 or 4. Does that help? Okay, and then recursion.
About recursion, I was thinking of something like this.
But the only problem is that we haven't seen sum yet.
But we can define
It. Yes, yes. Sum is built in, but let me hide it. So sum sums the elements of a list. So let's just define our own. Let's keep it simple for ints.
Yeah.
So if we have a list of ints, it sums them up. So again, that's like a reminder of yesterday. So to define something on list, we would define it for the empty list and for the non-empty list. So the sum of no elements is 0. And the sum of a list with a head and a tail would be x plus recursively summing the tail. And why do I get okay, ignore that. No, because fold R and yeah. Right, and we can try that out. So sum of the first 100 integers, as Gauss told us. Why? What? Did I save it? But I did hide it, I thought.
Maybe 6
I must.
polymorphism type classes.
Oh, data list sum. Okay, okay, fine.
Because you already imported data list.
Yeah, okay, I can't.
Close it and reopen,
Yeah,
or no?
yeah. Sorry about that. Right, so 50-50, so that works. And now we can, I think, Robertino was suggesting to show how that is, like with 1, 2, 3, for example. So sum 1, 2, 3. Right, so the compiler, whatever, sees this and first must pick the right equation. So in this case, it must check, is this an empty or an non-empty list? So it's a non-empty list, so the second applies. So I mean, sorry. So I mean, actually this 1, 2, 3 is just syntactic sugar for 1 colon 2 colon 3 colon empty list. So it's the second case. So x is 1 plus sum, and xs is the rest. So 2 colon 3 colon this. So 1 plus. So now recursively sum called itself again. So again, now I must evaluate this. And again, I have 2 possible equations. So I start at the top, which one fits? Again, it's not the empty list, it's the second case. So now 2 is x and 3 colon empty list is x's. So it's 2 plus sum 3 colon x's. Okay, now I'm still not done. Again, recursively called sum, the function I was just defining. So I must again now evaluate this. Again, 2 possible equations. Check whether the argument is the empty list or not. It's not, because there's 3 colon. So it's again the second equation. So the x now is 3 and the xs is this empty list. So it's 3 plus recursively sum of the empty list. And now I'm still not done, because there is still a sum to compute. But now the sum of the empty list, now the first equation applies. So it's 0. And then, I mean, Haskell knows how to do arithmetic on ints, so then it simplifies that to 6. So that would be an example of recursion. Is that okay? What?
Yeah, thanks. That's very clear. So that be the same case for does the process occur in the same way for a simple data type, right? on the constructor, leaf pattern match.
Yes. Yes.
Yes.
So what would be the best case for a construct for a custom data? What would be the best case?
Right. So the
Yeah, I understand. I think. I mean, for example, trees. If we have, I mean, we could, for example, I mean, we have our tree type. What was it called? Tree. Is that a good example? I think that's a good example, right? Should I also flatten or whatever? Yeah.
yeah, small one.
Yeah. So yesterday we had this flatten function, takes a tree, converts it into a list, and to flatten a leaf, it's the list with one element, and to flatten a node with left and right child, we flatten the left child and concatenate it with the right child, flattened. And now if we want to, for example, flatten node, node leaf 1, leaf 2, leaf 7. Just a second. I just want to try.
Need to name it, I think.
Yeah, exactly. Example. Just want to see whether it works. Okay, so that's fine. And now let's see. Okay, flatten. So the argument to flatten, so we have two, I mean, this is now very similar to lists because it also has two constructors. But I mean, we could also use this eval type from yesterday. Maybe that would have been better.
Yeah, but this is cool because
It's double recursive, yes. So it's not a leaf, it's a node. So we are in the second equation. So it's flatten of the left child and of the right child. What's the left child? That's node leaf 1, leaf 2, plus plus flatten of the right child, which is leaf 7. Okay. So the first flatten here is again the node case, so it's again recursive. So that's so we must flatten the left child, which is leaf 1, concatenate it with flatten the right child, which is leaf 2. And here this part, we are already in the first equation. It's a leaf, so it's the singleton list containing the 7. And now this flatten leaf 1, it's the first case. So it's the singleton one containing 1. And the leaf 2 is 2, 7. And now we would just, I mean, we also defined this plus plus. So now we could do that as well, but maybe not because it's lists again. To figure out that that is indeed the list containing 1, 2, and 7. So this is another, I mean, a custom data type tree in this case. And the base case in this case is leaf. And the node is not, it's recursive because in the node constructor you have arguments of type tree again. So you have to recurse again. Okay?
Should we do another example? Or?
I think the 50 minutes are up that I got.
Oh,
Okay.
okay. Okay, that's it then?
That's it then. But if you have more questions, I mean, you can always ask them either on Discord or tomorrow. I mean, also before we start with the lecture. Or I'm always happy to do examples. Yeah. Okay, then let's stop for today, right? Yeah.
Last question.
Yes.
The assignments. So can we make commits work in progress?
Yes.
Or do we need the whole thing complete?
For sure, yes. Just make commits I think the deadline, because like at some point we have to put a deadline because else we will like be grading the first exercise in a month. It's on Sunday evening, like almost like Monday morning for the people that like to work during the night. And so up until then you can like push commits or as often as you want. Like we will like we'll maybe look at it, but we won't say anything and let you work. Yeah.
But your question was about commits, not push, or did you mean push?
Well, push, yeah.
Yeah.
Okay. I mean, of course, you can have as many commits as you like, and you can also push several times. Yeah.
Yeah.
Just to wait, the Sunday is for way too long.
Sorry?
The Sunday deadline is for way too long.
Both and likely the rest of the exercises were for this week. Because we want to make sure you like learn the first week before going to the second. And if there's a big chunk of people that are kind of like not getting like some specific part or whatever, we're going to take the second week to go over that again before continuing. Just like we won't continue if like most of the class. That's the point, right? And if it's too easy, tell us and we're going to speed up.
Ideally, all tests should pass.
Sorry?
Ideally, all the tests should be passing, right?
Yes, if all test passes, likely you did everything right. It will be strange.
It could still be that we would criticize something
Yes.
stylistically, but of course, if all test passes, would be very good.
If once it works, if I think that we should prioritize like if that works, compiles it works. Because if you already did that, then maybe you could take your time to look if like you can do it more with less functions, with less recursion, whatever, right? Like make it look better. Because also like if less code means likely less bugs and means easier to understand for the next developer or you in like 5 months. So that's why it's like also a thing to take into account, not just that it works.
Okay?
Yeah.
Let's eat.